Okay, one last example on related rates. Triangle ABC is a right-angled triangle at the angle A, and AB is 20 centimeters. The angle ABC, okay, increases at a constant rate of 1 degree per minute. At what rate is BC changing at the instant when ABC, the angle ABC, measures 30 degrees? Okay, so step one, we got to figure out what's happening. So let's start with a diagram to help us understand what's happening. Okay, so we have a right-angled triangle, and it's right-angled at A, so let's call that A. Let's call that B, and let's call that C. Okay, here at angle ABC, we probably have a variable since this will be changing, right? This will be changing at a rate of 1 degree per minute. So this will probably be a variable, so we'll call that theta. We know that AB is 20 centimeters, so that's one of the constants in this problem. That's not going to be changing. That's changing. What else is changing? At what rate is BC changing? So BC is changing, and that's what we want to find. So let's call that X. Okay? And we'll call that in centimeters. At what rate is this side going to be changing at the instant when ABC is 30 degrees? Okay, so when theta is equal to 30 degrees, what is the rate of change of BC? So what would dx dt be? That's really the question. Okay, so this is what we need to find out. We need to find out how fast this is changing when this is 30. Okay, so let's see. What do we need to know? We also know d theta dt, don't we? D theta dt is right now 1 degree per minute. Okay. Now this should probably raise a red flag here, because if I take the derivative of a angle, in this case I'm probably going to be using a trig function, and this problem is probably going to involve the use of a trig function. So when I take the derivative of a trig function, I need to make sure that my angle is in radians. So this will probably have to change later on. Okay, but let's start by defining the relationship here. Okay, what relationship do we have here? It's actually pretty simple. Okay, it looks like I have a cosine relationship, so it's going to be the cosine of theta is equal to let's see, adjacent over hypotenuse, so it'd be 20 over x. So here's my relationship. Okay, very simple. And let's rewrite that as 20x to the minus 1, just to make differentiating a little bit easier. Okay, so if I differentiate this side and I differentiate this side with respect to t, since we're always talking about rates with respect to time, what's the derivative of this? That would be minus sine of theta. And since we're differentiating with respect to time, we have to use a chain rule and do d theta dt. Okay, so right now, the units of this, when I derive it, it's automatically going to assume these are in radians. So this would have to be in radians. So that means this will have to change because right now it's in degrees before I plug it in, right? Okay, what about this side? This side becomes minus 20 x to the minus 2 times the derivative of this with respect to time, dx dt. Okay, so here's my differential equation. Now I'm almost done. This is probably the hardest part. This part and this part are probably the hardest parts here. Okay, so once I find this, now I'm ready to start plugging in. But let's see, what am I missing here? I'm missing an x. Okay, I have an angle. I have this, okay, but I just need to convert this into radians. I don't have this right now, and this is what I'm looking for. Okay, so I need to find an x, and I need to convert this into radians. So let's convert this. Let's convert this into radians. What is 1 degree when converted into radians? That would be, since I have degrees on top, I would want to have degrees on bottom when I multiply. So it'd be in pi radians per minute times 1. So that would just be this would be in radians per minute. Okay, so now I have this ready. I have this ready. I need to find my x. So what is x? Well, I'm just going to use my original relationship here to find what x would be. So let's find that over here. Okay, cosine of at this instant I have 30 degrees. Okay, equal to 20 over x. So x would be equal to 20 divided by cosine of 30. What's cosine of 30? Well, sine of 30 is 1/2, so that would be root 3 over 2. Okay, and so x would be equal to 40 over root 3, and this would be in centimeters. Okay, so now I'm ready to plug that in. I have minus sine of 30 degrees times pi over 180 equals minus 20 times, now this is going to be on the bottom here, so that's going to be 1 over, let's see, 40 squared over, that would be 1600, 40 squared over, this would be normally on the bottom, that would be a 3, so I'm just going to move that up to here, okay, and this would be dx dt, and that's what we're looking for. Okay, so now I just solve for dx dt, and this becomes sine of 30 is minus 1/2, so this becomes minus 1/2 times pi over 180 equals, and this will cancel, and we end up with 60 on top, so we have minus 3 over, that's minus 3 over 80 dx dt. Okay, and now I solve for dx dt, so dx dt would become, and if I move this all over to the other side, we get approximately, and I could probably start using my calculator here, this would be approximately 0.233, and this is going to, what are my units going to be? This is length over time, so it would be centimeters over minutes. All right, so this would be my answer. This would be the rate that I'm interested in at the time when when theta is 30 degrees. Okay, so notice here it doesn't really matter what I plug in, whether I plug in degrees or radians in here, because this is just a ratio. It'll come out the same anyway. But this does matter. Okay. All right.